Yeah, hello students. I hope you will be able to listen to me. Good evening, Tarkeshwar. Good evening. Good evening. So, Tarkeshwar, I had first news that we have started a new batch, that is rank booster course for GATE 2021 batch B, mechanical engineering, and that batch has already been started on 16th of November. In this batch, Gil sir, myself Rajeev Singh, Aditya Gupta, Ashish Phutan sir, Deep Sangeet sir, Varun Singh sir, and Sagar Sharma sir will be teaching you all the different subjects. If you want to subscribe, you can use this referral code RK007, which will avail you 10% discount. So let's move into this next session of casting. In the last session, students, I had discussed about riser design. Yes. Now I am going to discuss about sprue design, and I am covering all these numerical aspects of casting chapter. You see what happens as we are. You are a plus student, Tarkeshwar. Great. Trying to design a sprue. You know, a sprue is that vertical channel, right? And there on the top, there will be this pouring basin, and then from here the molten metal will go towards the runner, right? So let us start the design of this sprue, and let us suppose that the sprue that we have is like a straight sprue having uniform cross-sectional area. So this is the way that vertical channel sprue is there, which will feed the molten metal to the runner, and this is our pouring basin. So what we do, we pour the molten metal into the pouring basin, right? So molten metal is right here, we have poured it, and then molten metal flows down into the sprue cavity. Let us say that the height of this pouring basin is h1, and that of the height of the sprue channel, that vertical channel that I have drawn, is h2, and let us say total height is h1 plus h2, that is your ht. Okay, so I have been taking this as h2 and this as h1 and this as h1, and total height h1 plus h2, let us say, is ht. Now thanks Tarkeshwar, thanks a lot. So you didn't come in live classes, like very lesser time you come in live classes, na Tarkeshwar. Yes, undoubtedly metal cutting and everything is awesome. The topic itself is awesome, and if someone knows the basics of those topics, then yes, uh, the flow of the chapter becomes like anything. No problem, Tarkeshwar. If you are getting doubt, you can come to any live class, right? And that is most scoring one, because from machining and machine tool and metal cutting they will ask 4 to 5 mark question. So let us concentrate here. Yes, Tarkeshwar, yes, thanks for your kind words, because very few people will be able to recognize what have I been teaching in those topics. Not everyone. Let us say this point here is 1, and P1 here is atmospheric pressure, right? Let us take that gauge pressure 0, and here let us say the molten metal, whatever amount of the molten metal is coming down, the same amount of molten metal is being poured here into the pouring basin with the help of the ladle. So what happens if you do this, then the velocity at point 1 will also be 0. Yes, and next Here let us say this is your point 2 and this is your point 3. You know, point 3 is also open to atmosphere, because down here there will be this, you know, what will be this? This will be the splash core, and from here the molten metal will go towards the runner cavity. So surrounding is what? Sand mold only. So this is like open to atmosphere, na? So point 3 will be open to atmosphere. Yes, if point 3 is open to atmosphere, so undoubtedly pressure at point 3 will also be 0. So pressure at point 3 is 0, and we have assumed that this sprue is having uniform cross sectional area. While we are designing the sprue, we are assuming that sprue is having uniform cross sectional area. So dear students, if you apply the continuity equation, you can write A2 V2 is equal to A3 V3, or you know, we have assumed that the design that we are doing in such a way that the cross sectional area of the sprue is same. So A2 and A3 will be cancelled. V2 will be equal to V3, right? As V2 is equal to V3, my dear students, we can apply the Bernoulli's equation, which will give you P2 by rho g plus V2 square upon, let me write it here, okay? Otherwise, it might not be visible to you. P2 by rho g plus V2 square by 2g plus head of point 2 is from datum. Let us say this point over here I am taking as datum, that will be equal to P3 by rho g plus V3 square upon 2g, and plus from datum the height is 0. You see, since V2, yes, Tarkeshwar, since V2 and V3 they are equal, we can simply neglect these terms, and you know, P3 is 0, so this will become 0, or P2 will become minus rho g H2. Yes, P2 will become minus rho g H2. What does it mean? This means that pressure at point 2 became negative pressure, right? This is what happened. If you keep the cross sectional area of the sprue constant, at point 2 the pressure will become negative. And that, what is the significance of negative pressure? The significance of negative pressure is like, dear students, you see, you used to have coconut water, na? Or you used to have maza, right? Or slice. So you will have a straw. You suck that maza or slice or that coconut water through that you know, straw. So what happens here? Here you apply a pressure in such a way that down there at the other end of the sprue, what happens? A negative pressure is created, even lower than the gauge pressure, and that is how what happens, even the remaining droplets of that spice or that slice or maja or coconut water that you like inhale, you drink, right? So that is what happening. This will, you know, appear like you are sucking out the metal, like from here point 3, you know, at point 2 molten metal was coming under gravity, but if you keep this cross sectional area constant, then it will start feeling to you like you are sucking the metal like this. At point 3 you are sucking it. So what will happen? Molten metal was coming under gravity, but since you are, you know, sucking the metal from here, and that is what happening. Since point 2 pressure is becoming negative, means what? At point 3 you are applying some extra load, right? That is the suction pressure. So what is happening? Apart from the molten metal from here, as you can see, apart from molten metal from here, from the surroundings, you know, air will also start getting sucked in. And if air starts getting sucked in, what will happen? This air may dissolve into this molten metal, and later on it can reach to the mold cavity, and there, once the casting is solidified and that air that was dissolved into it was trying to come out, and let us say it didn't come out, so that air will be entrapped. And if air is being entrapped into the casting, that will lead to several gaseous defects. like blowholes can be there, blisters can form, pinhole porosities can occur. Yes, so this is what, yes, learned mechanical, this is what we call as aspiration effect. That means to avoid this aspiration effect, what will have to be done? We'll have to change the cross sectional area. We will have to change the cross sectional area, let us say, and we'll have to change the cross sectional area in such a way that pressure throughout this sprue remains constant, isn't it? Then only that aspiration effect will not take place, and that is why we actually change the cross sectional area of the sprue. Let us say now we change the cross sectional area of the sprue, and the sprue is something like this. Okay, and we change it in such a way that pressure throughout the sprue remains uniform, and it must remain uniform, otherwise any pressure difference may cause aspiration effect. So let us say this point 1, this point 2 again, and this point is 3. So I have my dear friend over there, learn mechanical. Do we know each other? Learn mechanical, as I can see you there in the chat section. Do we know each other? Learn mechanical. Now, you know, A2 is not equal to A3, and pressure throughout the sprue is uniform, so P2 is equal to I'm sorry dear, actually I got cough and cold, but for many days I was not taking these YouTube classes, and I had assured all of you that I will take, so I am taking. Okay, learn mechanical, what's your real name? So P2 is equal to P3, A2 is not equal to A3, so if you apply the continuity equation, A2 V2 is equal to A3 V3, A2 A3 cannot be cancelled anymore, A2 A3 cannot be cancelled anymore. So what we can write is V2 is equal to A3 upon A2 into V3, and let us say V2 is equal to R V3, where what is R? Where R is A3 upon A2, this area ratio A3 upon A2 is R. Now we are saying that ki R is the area ratio to avoid aspiration. What is R? R is the area ratio to avoid aspiration. So if you now apply the Bernoulli equation, you know, you can write that P2 upon rho g plus V3 square upon 2g plus, you know, this height again is from there to here, this height is h2, is equal to P3 upon rho g plus V3 square upon 2g, and plus 0.3 is at datum, let us say. So this, so P2 by rho g and P3 by rho g will cancel out, because we have already assumed that since this aspiration thing has not to happen, so pressure throughout the sprue must remain uniform. Now V3 square upon 2g, sorry, here it is V2, I'm sorry dear students, here it is V2. Yes, so V2 square upon 2g plus H2, this will become equal to V3 square upon 2g. What I am doing is, in place of V2, I am putting this RV3 over there, okay? So this will become R square V3 square upon 2g plus H2 is equal to V3 square upon 2g. Or this, if you simplify, you can easily write that R square minus 1, let us take it common, multiplied by V3 square upon 2g is equal to minus H2. Yes, or this R square, just a minute, this R square minus 1 will become minus 2gH2 divided by V3 square. Yes, or R square will become 1 minus 2gH2 upon V3 square. You see, we know what is V3. V3 is equal to, here 0.3, V3 will be equal to square root of 2gHT, where HT is what? Total height, H1 plus H2, this is H1, H1 plus H2 is equal to HT. Yes, great. Sir, can you share your question on metal cutting and metal science? I haven't plus subscription. Learn mechanical. What can you do is you can join a Telegram group. Its name is Mech Army. Okay, though you are not a plus student, don't worry. You will get every single question from there and every single notes. Whatever have I taught there, all those notes are available in that Telegram group. Simply go to Telegram, you search this group Mech Army, yeah? You will get that. Whatever you need. By the way, what's your name? Learn mechanical. You didn't say. Chalo. Next. This, if you simplify, this will become 1 minus 2gh2 upon v3 square means will become 2ght, and this was equal to actually r square, right? Look at the previous slide. Yes, this same thing I have written, only v3 square have I replaced by, yes, square root of 2ght. So this became 2ght. Now 2g and 2g will be cancelled. Very simple. What are you getting? R square is equal to ht minus h2 upon ht. And if you do ht minus h2, look at this. If you do ht means and minus h2, this will be h1 only. Yes. So this will become r square is equal to h1 upon ht. So r is what? A3 upon A2, na? A3 upon A2, and this will be a square root of H1 upon HT. Directly you can remember this formula. If they ask you to solve the question and to find the spew dimensions by avoiding aspiration, simply remember this formula. This is going to be very much important for you in your GATE exam. This thing you must remember, apart from the riser design thing that I had said, and I told you that in the last lecture. I told you that this Keynes method is going to be very much important for this year, right? Keynes method. Now I am going to tell you about this filling time. This also you remember. You see, I am not going to say every single specific thing. It's a crash course type of thing. I am only telling you the important things. Gate, if you are using, a top gate, what you will be doing? You will have this filling time through top gate as equal to volume of casting divided by discharge. And this you can write in different terms. Volume of casting is, let us say, volume of casting, let us say VC. This will be like cross sectional area of the casting multiplied by height of the casting. Or if it is having some complex intricate type of shape, then there will be some other method to find the volume of the casting. That is how you can find the volume of the casting. Now divide by discharge. Discharge means the discharge is equal, right? Continuity equation. This can be either through the gate, discharge is this Ag into Vg through gate, or this can be like discharge through the runner, or this can be like discharge through the sprue. Anything, whatever the given data is there, that you can use to find this discharge. One more thing, they can give you like something called a choke area. For now you just keep this in mind. Choke area is the one area which is the smallest in cross section, right? So there also choke area multiplied by VC, if you do, AC is your choke area, the minimum possible area in this whole channel of sprue runner and gate, and VC will be velocity at that choke area. This also they can ask you. So do not think like what is this choke area alien term coming here, right, my dear students? This you must remember for top gate. What is this top gate, my dear? Suppose your sprue is like this, your runner is like this, and you have the mold cavity, and cavity is like this. You can see the molten metal is right now filling from top. This is what you call as top gate. Okay, now the another thing is your through the bottom gate. If they talk about bottom gate is what? It's like you have this sprue and you will have this runner, and casting is like this is like your casting. Okay, and casting is having some height like let us say h, and this is having some cross sectional area like capital A. Let us say capital A is the cross sectional area, capital H is the height, and this is like pouring basin and everything here. Okay, and you know that this is like h1 pouring basin height, and this is like h2 your sprue height, and this h1 plus h2 you write like total height ht of the molten metal. Yes, so if they ask for this bottom gate thing na, simply you can go for kit filling time through the bottom gate will be ag divided by under root 2g ag, sorry, a into h divided by ag under root 2g. This is your ag, area at the gate. Okay, multiplied by square root of ht minus square root of ht minus capital H. This you remember. This already I have proved, right? Ki how does it come? So this you can remember for your bottom gate system. Chalo. These two formulas are very important. They can ask you question anytime. This is important. This formula, whole formula that I have written here, every single term, this, 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 everything is important. Yes, you must keep this in mind. Now, my dear students, let me talk about something called as this solidification. And here I will be telling you about 1 mark questions like chills, chaplets, what are the different types of solidification. You see, types of solidifications are like directional solidification or unidirectional solidification. What is this unidirectional solidification? Let me just explain this to you. Unidirectional solidification. Suppose you have this mold cavity, okay? In the mold cavity you have the molten metal, and there you have the sprue cavity or the riser cavity, anything, either the riser or the sprue, anything. Okay, now in the beginning what will be there? This will be whole molten metal thing. Yes, now solidification will begin. As the solidification begins, my dear, undoubtedly the solidification will begin from the boundary. As the solidification begins, undoubtedly the solidification begins from the boundary. Yes, now here this layer will solidify. Just a minute. From where did this come? Yes, here this layer will solidify, and now suppose these solidification fronts are moving in this direction like this. This is how it is solidifying. This is how it is solidifying. This is like moving in this direction. This is like moving in this direction. So as the solidification move, fronts are like starting from the boundary and moving towards this direction. This is like either your sprue or your riser. So what is happening? Look at this. Look at this, my dear students. Look at this. Here. Here there is a molten metal. Yes. Can you see? Here there is a molten metal. And as it is solidifying, you know, its volume is reducing. As it is solidifying, its volume is reducing. As the volume is reducing, that volume which is reducing, that shrinkage which is happening, that is compensated by the molten metal present into the riser. That is compensated by the molten metal present into the riser. Molten metal comes back, and whatever amount of volume shrinkage has occurred here, it compensates. Right? So no problem at all. Everything will solidify, cool nicely. Nothing, no problem. Right? Moreover, this type of solidification that we are calling as unidirectional solidification, that from mechanical tech talk. Hi. So as the solidification fronts are moving from the surface and it is moving towards the sprue or riser section, you are saying that this is unidirectional solidification. This also helps you in purifying the molten metal. Suppose here in that molten metal there was this impurity, there was this impurity. Few of the impurities you filtered into the strainer, few of the impurities were filtered into the skim bob, that already I have explained in the first lecture. Now there may be remaining impurities. Now if the solidification happens like unidirectional, the way I have shown you here, like it starts from the surface and all the solidification fronts, they move in one direction, that is either towards the sprue or towards the riser, you are saying that the solidification is unidirectional. How will you say that this is helping you in purifying the metal? Suppose if these impurities are there remaining into the molten metal, then you guys just tell me, these impurities, solid impurities, will be more soluble into this solid state of the metal, or they will be more soluble into the liquid state? These impurities will be more soluble into the solid state or liquid state. Undoubtedly these impurities will be more soluble, will be able to dissolve in a better way into the liquid state, right? They cannot be soluble into the solid state. So as these solidification fronts, let me show you, are forming and moving towards the sprue or the riser, as these solidification fronts are forming and moving towards the riser, as these solidification fronts are forming and moving towards the riser, let me just show you, just hold on dear. As these solidification fronts are forming and moving towards the riser, here this is your like a riser, or it can be a sprue even. So what is happening? Suppose there was a impurity here. So as the solidification fronts formed and this solidified and moved into this direction, so these solidification fronts will push these impurities in this direction towards the liquid state, and the same thing will keep happening, right? Because impurities are not that much soluble into the solid state. So these solidification fronts will be forming and will be moving towards this direction. So meanwhile, whatever the impurities are there, they will be pushed away by these solidification fronts. They will be pushed away by the solidification fronts, and these impurities will reach here at the end of the cavity, right here. And this solidification happened. So this is what going to be your casting na. So later on you can simply cut off this part na. And this whole thing will be scrapped off. So you came to know that unidirectional solidification also helps you out in what? Purifying the molten metal, right? And another advantage is, as the unidirectional solidification happens, no problem occurs. Like from one side to another side, the solidification fronts are moving, so no shrinkage type of problem will be there, because every time this is moving in this direction, some volume reduction happened here. From riser, the molten metal will come back and will compensate for the shrinkage. Yes, so that is why unidirectional solidifications are preferred. Now my dear students, you see what will happen. Let us look at bidirectional solidification. Yes, that is another type of solidification which can happen. Bidirectional solidification. What happens in bidirectional solidification? Let us look at this, my dear students. In bidirectional solidification case, suppose you have this mold cavity. Let me just draw it fast. And on the another end, you have this something called as a sprue or riser. Anything can be there. Huh? Now, molten metal is there. Solidification begins. Undoubtedly, solidification will begin from the boundary itself. Yes, the solidification will begin from the boundary itself. Like from here, the solidification begins from the boundary itself. These solidification fronts, whichever formed at the boundary, they will start to move towards this direction, that is towards either the sprue or the riser. Yes, in this direction they are moving. Now something happened, some problem occurred, like the shape of the casting was as such that the thermal gradient which developed there, that led into the formation of one another solidification front, you see here. Now due to that, you know, non-uniform thermal gradient, suppose this solidification front formed here, means solidification also started at that point, this solidification front will start to move towards, you know, this direction, towards that direction, towards this direction. Now as it is moving, means it is increasing its size, and this solidification is front is moving in this direction. What will happen after some time, you know, this road through which the molten metal from the mold cavity, sorry, from the sprue cavity was coming back to compensate for the shrinkage which may happen here, this itself, this road itself has been blocked. So even though molten metal has been present here, molten metal is present here, this molten metal will cannot come back. Yes, this molten metal cannot come back to compensate for the shrinkage which will happen, in between the space of the primary solidification front, and the secondary solidification front. Yes, so this will solidify, ultimately this is going to solidify, but as this will solidify, there will be some, you know, reduction in volume, and that reduction, let me show you like this. By erasing this much, you will understand this reduction is going to be like this much of portion, that whatever the liquid was there, it solidified, right? And now what happened, this type of empty space is there, this type of empty space is now there, which cannot be compensated anymore, because the road through which, the route through which, the path through which this molten metal, you know, from a sprue comes back and compensates for the shrinkage which is happening here, that path has been blocked by what? By the secondary solidification front. Now what will happen, this will lead to a problem here which you call as shrinkage cavity. This shrinkage cavity will be a defect into the casting. This should not happen. So how to take care of this? For this, what we'll be doing, we will try to do something that this secondary solidification front does not form, or we don't give enough time for this secondary solidification front to form. How to do that? To do that, we will increase the rate of formation of and movement of this primary solidification front. How to increase the rate of formation and movement of this primary solidification front? For that, my dear students, let us look at this. Let me erase all those things. Let me tell you what we do. We use chills. Chills are what? Chills are actually the metallic plates having high melting point and very high thermal conductivity. What happens when you use the chill? When you use the chill, you use that chill like, you know, it will have a shape and size which will fit into the cavity and can be kept adjacent to the cavity very easily at the required locations. Like, let me tell you, this is how you can put the chill. You see, this the solidification front was, you know, moving, and there you kept a chill like this. This is a metallic plate, let us say. So molten metal will now directly come in contact with this metallic plate. So the movement of this solidification front, primary one, will become very fast. So it will not give any time for the formation of the secondary solidification front. And that is how this bidirectional solidification, which may result into a defect called as shrinkage cavity, can be avoided. Yes. Now there is another type of solidification, which is what we call as progressive solidification. What is this progressive solidification? That let me tell you. Suppose you have a mold cavity which is like, it is having a thin section in between, and on the ends there are the thick sections. This is like a thin section here, this is like a thin section here. Oh, oh. This is like a thin section, and on the ends there are thick sections like this. On the ends there are the thick sections, and the thick sections are provided with risers, and the thick sections are provided with risers. Here there is a riser, here there is a riser. Riser has been provided there to compensate for the possible shrinkage during the first two stage of the solidification, that is from pouring temperature to melting temperature and from melting temperature to freezing temperature. This is all liquid metal here, this is all liquid metal here, let us say. Okay, so there, this is a liquid metal. Here the volume of the metal is less, this metal section is thin. Now what will happen? Undoubtedly solidification will start here. This thing will start to solidify from this side, and this thing will start to solidify from this side. This solidification front will move like in that direction, and these solidification fronts will move in this direction. So later on, after some time, what will happen? I'm sorry, a lot of cough and cold is there, but I am going like unstoppable. Huh? Yes, since I am enjoying this, that's why I'm not feeling this pain of cold and cough. By the way, I'm a guy, if he gets the cold and cough, then God can only save me. That is how I feel. But if I teach, like, I forget everything. So now these solidification fronts will move in this way. You see, that is how this will happen. Now, this way the road has been blocked. This way the road has been blocked. The molten metal cannot come back and cannot compensate for the shrinkage which will happen here. Here also there is a molten metal which will solidify, but and solidify and will shrink, but there will be nothing to compensate for it, because these two roads has been blocked. These two routes have been blocked from where the molten metal can come back and compensate for the shrinkage. This road itself has been blocked because here the solidification has taken place. So what will happen later on? You will find this much of section which after solidifying will remain empty. Yes, because of the shrinkage which occurred there. Yes, are you getting me? Because of the shrinkage which occurred there. So this much of section will remain like empty. If you do the X-ray, you will find that this empty section is there. So this is what we call as shrinkage line cavity. This is what we call as shrinkage line cavity. And this shrinkage line cavity happened due to what? Due to this type of solidification. Yes, and that is what we call as progressive solidification or parallel solidification, right? Because one solidification front started to move from this side, another solidification front started to move from that side. Parallelly they were moving, right? So this is what we call as progressive solidification or parallel solidification, and this progressive or parallel solidification will lead to a defect which just now I discussed is called as shrinkage line cavity. Is called as shrinkage line cavity. So to avoid this shrinkage line cavity, what to do? You see, this is happening because the thermal gradient is as such over there that it is leading to something called as progressive solidification that I had discussed to you just now. So this leads to what? Shrinkage line cavity. This word you should remember. Progressive solidification leads to shrinkage line cavity. To avoid this, what you do? This is the sand mold in which you have created actually this cavity. Yes. So instead of making the thinner section like this, the thinner section, you see, what we'll be doing, we'll be tapering it towards the thicker section. This is how the cavity will be made, tapered one. So that, now if you make it like this, you can easily understand. This is the molten metal right down here, right down there, the molten metal is there. Yes, this is the molten metal. So as the solidification will start, this solidification fronts, you can easily understand, will move like this, and this is how the solidification will take place. So every time, from here the solidification moving in that direction, from here the solidification is moving in that direction. So every time liquid metal will be present for any shrinkage which will take place. Later on, when this solidification has completed, after tapering this section, solidification has completed, then no problem. Later on, now my dear student, you can machine this much of extra metal. Later on, you can machine this much of extra metal out, right? So, making the cavity tapered in a way I have shown, that is from thinner towards thicker. You see, from thinner towards thicker, from thinner to this I machine. Now you have your casting, whatever you wanted. So tapering this thinner section towards thicker is what we call as padding. So how is padding provided? By making the thinner section tapered towards the thicker section, right? That is what, and that is the cavity shape here. That is what you call as padding. Yes. So paddings, chills can be used to convert the different types of solidification process named bidirectional solidification and progressive solidification towards the unidirectional solidification. Especially if you name, then chills are used to convert unidirectional solidification, bidirectional solidification. Chills will convert bidirectional solidification into unidirectional solidification, and padding will convert progressive solidification or parallel solidification into unidirectional solidification. During casting, what is best? Unidirectional solidification is best. So though if the other different types of solidification is happening, we will try to make it what? Unidirectional. Yes, my dear students, no problem at all. All of you understood this? So I had given you a very good revision on this topic. Tomorrow, by the way, the schedule is there, but I will not be able to take the class because tomorrow evening I am flying from Mumbai to Patna. Yes. What you can do is, you can meet me day after tomorrow. I will start this welding also. So this crash course will go on. Like regularly. On regular basis I will take. And once I will reach Patna, instead of taking this way, I will be taking all these classes on a smart board. Because there, that house that I have in Patna, I have this smart board installed over there. So that will give you another type of feel and you will enjoy the lectures in a better way. By the way, meanwhile, if you are trying to, or if you are planning to subscribe for Unacademy, yes, you can use my referral code RK007. Meanwhile, you can join the Telegram group Make Army for the regular updates of my classes, notes, questions and everything relevant to your GATE exam. Thank you guys. See you soon tomorrow. Okay? No, sorry, day after tomorrow in this YouTube. Okay? And that will be there on a smart board. See you all. Bye bye. Tata.